A team of scientists just put a date on the end of the world for one of Europe's oldest cities. Not a prediction, not a prophecy, a mathematical calculation, a deadline written in the language of physics for when the ground beneath 500,000 people will reach its absolute breaking point. The year is 2030. The earth beneath the Italian city of Naples is not solid, it's stretching, and where it's stretching the most, right over a vast, hidden chamber of magma, the crust is approaching what physicists call a finite-time singularity, a point of no return, a mechanical failure on a geological scale. And here's the part that should keep you awake at night. These new calculations, published in May of 2026, don't just say it might happen. They say it is the inevitable outcome of a process that has been accelerating for 20 years. What does that look like when it happens? Let me know in the comments what you think the first warning sign would be. Most people, when they think of Naples, they think of this: Mount Vesuvius, the iconic, cone-shaped killer of Pompeii, the villain that has haunted this coastline for 2,000 years. But the real danger, the one that has volcanologists at Italy's National Institute of Geophysics losing sleep, isn't the mountain you can see. It is the flat, unremarkable ground that 500,000 people are standing on right now. An incredible amount of research goes into making these documentaries. Over 90% of our viewers aren't subscribed. If you find this story as critical as we do, please take a second to hit that subscribe button. It ensures you won't miss the next update, and it's the single best way to support what we do. Let's begin. This is Campi Flegrei, the Phlegrean Fields. And it is not a mountain. It is a 15-kilometer-wide supervolcano, hiding in plain sight. A sprawling, underground plumbing system of magma and superheated gas that is waking up. The ground here is breathing. In a process geologists call bradyseism, the earth itself is rising and falling, like a slowly inflating lung. Since 2005, the center of the nearby town of Pozzuoli has been lifted 1.4 meters, 4.5 feet. The port is rising out of the water. The foundations of buildings are cracking, and thousands of small earthquakes are shaking the residents every single month. They are living on the roof of a pressure cooker. And scientists now believe that the lid is about to blow. The question is no longer if the crust will break. It's what happens on the other side. Did a team of geophysicists just give this region a 4-year warning to evacuate? Or did they just witness the final, frantic breaths of a monster before it erupts? To understand how a major European metropolitan area ended up in this impossible situation, you have to go back 40,000 years. Before Naples, before Rome, before civilization. Campi Flegrei produced an eruption so violent it has few equals in the history of the planet. The Campanian Ignimbrite eruption, a volcanic explosivity index 7 event. It wasn't an eruption, it was a geological reset button for the European continent. It blasted hundreds of cubic kilometers of ash and rock into the stratosphere, triggering a volcanic winter that plunged the planet into a deep freeze for years. It left behind a scar on the Earth's surface, a vast, sunken depression called a caldera. That is what Campi Flegrei is, a crater so enormous, people built cities inside of it without ever realizing they were there. The supervolcano was born, but the trap was not yet set. That would come 25,000 years later, in a second, smaller, but critically important eruption. Around 15,000 years ago, the volcano erupted again, blanketing the entire region in a thick layer of fine ash. This ash, over time, mixed with water and hardened into a type of rock called pozzolana, a natural cement. The very same material the Roman Empire would later rediscover and use to build its aqueducts and harbors, structures so durable they still stand today. The volcano had, by complete accident, engineered its own prison. It had forged a dense, incredibly strong concrete lid over its own magma chamber. This is why Campi Flegrei is so dangerous. Most volcanoes have weaknesses: fissures, vents, pathways for gas and pressure to escape safely. Campi Flegrei's caprock is too strong. It doesn't leak, it doesn't vent, it flexes, it bends. The ground bows upward for decades, stretching like a steel plate, until the pressure from below becomes so immense that the rock doesn't bend anymore. It shatters, catastrophically. You don't have to take a scientist's word for it. The evidence is carved into the architecture of the ancient world. In the center of Pozzuoli stands the Macellum, a Roman market built in the 1st century. Its tall marble columns tell a story that no history book can. 7 meters up their sides, above the height of a modern two-story building. The smooth marble is riddled with small holes. These holes were drilled by marine mollusks, a species of stone-boring sea snail that lives only underwater. The columns are silent witnesses. They prove, with geological certainty, that the entire city of Pozzuoli has been on a slow-motion elevator for 2 millennia, sinking so low that the Roman market was completely submerged beneath the waves of the Gulf of Pozzuoli, and then rising so high that the sea snail holes are now exposed 23 feet in the air. The city is riding the roof of a breathing magma chamber, and right now it is only going up. It's an incredible story to follow. What's the most shocking detail you've heard so far? I read all the comments, so let me know what you think. The engine driving this geological elevator sits deep underground. At a depth of around 8 kilometers, or 5 miles, lies the main magma reservoir. Think of it as the furnace. For decades, the system was stable. But starting in the early 2000s, something fundamental changed. Highly pressurized fluids and gases, a volatile mix of carbon dioxide, water vapor, and sulfur, began to rise from this deep chamber. They didn't come all the way to the surface. Instead, they pooled at a much shallower depth, between 3 and 4 kilometers down, right beneath that concrete-like caprock. This is the shallow reservoir that is now pressurizing the system. It is the direct cause of the bradyseism that is lifting Pozzuoli into the sky. For years, the central debate among volcanologists was about what exactly was building up in that shallow chamber. Was it just superheated water and steam, a dangerous but potentially manageable hydrothermal system? Or was it fresh magma, being actively injected from the deeper mantle? The answer to that question changes everything. A steam-driven system might eventually run out of pressure. It might find a small crack and vent itself harmlessly. An active magmatic system does not stop until the magma itself finds a way out. In April 2026, sensors buried across the caldera gave a terrifyingly clear answer. They registered an all-time high in carbon dioxide emissions gassing out of the soil. CO2 is a key indicator. It's a gas that comes directly from deep, degassing magma. It was a chemical fingerprint proving that the monster's heart was still beating. A fresh pulse was coming from the deep. The pressure wasn't stabilizing. It was building. The ground wasn't just being pushed up by old steam. It was being inflated by the leading edge of an active intrusion. The system was live. This has happened before, and the last time it did, it built a mountain in a week. Let's be honest. The science here can feel abstract, but sharing this video with your family and hitting the like button makes this information more visible, helping everyone understand the real-world stakes. It's a small click that makes a big difference. The year is 1538. For decades, the residents of the Phlegrean fields had been living with the same signs we see today. The ground had been steadily rising. Earthquakes, small but persistent, had become a part of daily life. The shoreline had retreated, leaving ancient docks high and dry. Then, on the night of September 29th, the earth tore open. A fissure ripped through the flat ground near the medieval village of Tripergol, a small resort town famous for its ancient Roman baths. It wasn't a gentle crack, it was a violent rupture. A gaping mouth of fire, ash, and molten rock opened where fields and vineyards had stood just hours before. For 7 days, the eruption continued with terrifying force. It didn't build a cone slowly over centuries. It built a mountain, 130 meters high, almost 430 feet. Out of nothing, it buried the entire village of Tripergol, its ancient baths, its villas, its people. Gone, completely erased from the map. When the eruption finally stopped on October 6th, a brand new geographic feature sat smoldering on the coastline. They called it Monte Nuovo, the new mountain. This is what a small eruption at Campi Flegrei looks like. It does not just modify the landscape, it creates it. The 1538 event was a tiny VEI-3 eruption on the volcanic scale, a firecracker compared to the dynamite of the Campanian ignimbrite. But it still birthed a 40-story mountain and wiped a village out of existence in a single week. Now imagine that same event happening today, not in a field, but in the middle of Pozzuoli, in the suburbs of Naples. That is the baseline threat. A new mountain tearing its way through a neighborhood of 500,000 people. The memory of 1538 faded over the centuries. The volcano went quiet. The land slowly subsided. People moved back. They built over the caldera, forgetting the furnace that lay beneath their feet. Then, in the 20th century, the monster stirred again. Between 1982 and 1984, Campi Flegrei entered a state of acute crisis. It was the most intense period of bradyseism in modern history. The ground beneath Pozzuoli shot upwards by 1.8 meters, more than a meter in a single year. The uplift was so rapid and so violent that it triggered swarms of thousands of earthquakes. Buildings cracked, the ground fissured, the port became unusable. The daily tremors, the constant sense of motion underfoot, created a state of perpetual fear. The ING, Italy's Volcanology Institute, and the Department of Civil Protection feared a 1538-style eruption was imminent. A major fracture could happen at any moment. They made the only decision they could. They ordered a mass evacuation. 40,000 people were forced from their homes in Pozzuoli. They became refugees in their own country, moved to temporary housing, waiting for their city to either explode or calm down. They waited for months, then years. Businesses failed. Families were fractured. A city was hollowed out. And then, the uplift stopped. The earthquakes subsided. The magma, which had been pushing up from below, retreated. No eruption came. The crisis was over. The volcano had cried wolf. This created a new kind of danger, one that is not geological, but psychological. The people of Pozzuoli had their lives ripped apart by a false alarm. They endured years of displacement and economic ruin for an eruption that never happened. The authorities who ordered the evacuation were criticized. The scientists were accused of alarmism. An entire generation learned to distrust the warnings. This is the concept of evacuation fatigue, and it is the single greatest challenge facing the Department of Civil Protection today. If they issue an evacuation order in 2026 or 2027, based on the same signs they saw in 1984, how many people will refuse to leave? How many will remember the last crisis? The years of waiting for nothing, and decide to risk it. The science can be perfect, the predictions can be accurate, but they are useless if the public does not listen. A successful evacuation requires trust, and in 1984, the volcano broke that trust. The current period of unrest began quietly in 2005. A slow, almost imperceptible uplift, a few millimeters a month. But it never stopped, and it has been accelerating ever since. By early 2026, the cumulative uplift had passed 1.4 meters. The rate of uplift had increased to 10 millimeters per month and was still climbing. The seismic activity grew in lockstep. In May of 2025, a magnitude 4.6 earthquake struck, the strongest in 40 years, since the peak of the 1980s crisis. It sent terrified residents into the streets. Then, on May 21, 2026, a magnitude 4.1 quake hit near the coastal town of Bacoli, causing more panic and minor structural damage. The ground isn't just rising anymore. It's actively breaking. Each tremor is the sound of the rock cap stretching further, getting weaker, moving closer to failure. One of the leading experts on this process is Professor Christopher Kilburn from University College London. For years, his team has been studying the physical properties of the rocks that make up the caldera's cap. They don't just look at the uplift, they model how the rock itself responds to the stress. His conclusion, published in a landmark 2023 study, was chilling. The crust beneath Campi Flegrei has lost its elasticity. During the 1980s crisis, the rock could stretch and bend to accommodate the pressure. Now, after 20 years of continuous strain, it's becoming brittle. It is no longer absorbing the stress. It is accumulating damage. It is moving, as Kilburn himself stated, closer to rupture. The science was becoming alarmingly specific. Then, in May of 2026, two separate studies landed like bombshells, fundamentally changing the timeline. The first was a new, high-resolution 3D map of the volcano's entire plumbing system. Using data from over 5,000 teleseismic waves, the echoes of distant earthquakes traveling through the Earth, scientists at the ING were able to create an unprecedented image of the magma chambers. They confirmed the primary reservoir at 8 kilometers deep, but they also identified, for the first time, a discrete zone of partial melt, a pocket of active magma, in the eastern part of the caldera, at a depth of 10 kilometers. This wasn't just a schematic anymore. It was a CAT scan. It proved, beyond any doubt, a direct connection from the Earth's mantle all the way up to the shallow reservoir that is pushing on the surface. The entire system was connected and active. I know this is the second time I'm asking, but so many people love these deep dives and then just forget to subscribe. We have a ton of new investigations coming up, and hitting that button ensures you're the first to see them. It's a huge help. Thanks. The second study, and the one that made headlines around the world, came from a team led by Dr. Davide Zaccagnino, a researcher at INGI and China's Southern University of Science and Technology. His team took all the data, the ground uplift, the seismic frequency, the rock stress models, and applied a new type of mathematical analysis to it. They were looking for the underlying pattern. Was the stress increasing linearly, exponentially? The answer their model produced was neither. The system was obeying a much more terrifying physical law. It was accelerating towards what is known as a regularized finite-time singularity. That is a complex term for a terrifyingly simple concept. It means the system is not just heading towards a failure point, it is accelerating towards it in such a way that you can calculate when it will arrive. It's like watching a crack spread across a pane of glass. At first, it moves slowly. Then, as the stress concentrates at the tip of the crack, it accelerates faster and faster until the entire pane shatters in an instant. Zaccagnino's model suggests the crust of Campi Flegrei is that pane of glass. The stress is concentrating. The breaking point is no longer a theoretical possibility. It is a mathematically predictable event. Their paper did not give a single day. It gave a window during which the accumulated stress will overcome the strength of the rock. That window opens in 2030 and closes in 2034. This is a paradigm shift in volcanology. Scientists are no longer just monitoring a volcano. They are counting down to a pre-calculated moment of structural failure. The model predicts this failure will occur when the total ground uplift reaches approximately 4 meters. As of mid-2026, the uplift is at 1.4 meters, with the rate of rise increasing every month. The math is relentless. The deadline is approaching. So what, exactly, happens when the singularity arrives? What does the breaking point look like? Dr. Zaccagnino is careful to state that the model predicts when the crust will fail, but not precisely how. With the current data, there are 3 primary possibilities, ranging from concerning to apocalyptic. The first, and most hopeful scenario, is what's known as an aborted eruption. In this case, the crust does break. A significant crack or series of fissures opens up. But instead of providing a pathway for magma, it simply allows the vast quantities of trapped gas and steam in the shallow 3-kilometer deep reservoir to vent violently, but non-magmatically. There would be a massive release of pressure, loud explosions, and a huge plume of steam and gas. The ground, its pressure relieved, would then begin to subside. It would be a terrifying event, but one that averts the worst-case scenario. The pressure cooker's safety valve finally releases. The second possibility is a repeat of history, a 1538-style eruption. The rupture cracks the crust, and this time, the magma is in the right place at the right time. It finds the new pathway and ascends rapidly to the surface. Given the urban density of the area, this is a catastrophic outcome. A new Monte Nuovo could be born directly in a residential district, destroying everything for several kilometers around it. It would be a localized disaster, but an almost unimaginable one for a modern European city. The evacuation of 500,000 people would be a desperate race against an eruption that could build a mountain in days. The third possibility is the one that keeps national governments awake at night. The unthinkable repeat of 40,000 years ago. In this scenario, the initial rupture is not contained. It cascades. The failure of one part of the crust puts unbearable stress on the next, creating a chain reaction of fractures across the 15-kilometer caldera. This could, in theory, open a large enough conduit for a massive volume of magma from the deep 8-kilometer chamber to erupt explosively. A caldera-forming VEI 6 or 7 event. The scientific consensus is that this is an extremely low probability outcome. The conditions for such an eruption are complex and may not be present, but with a system this large and this pressurized, low probability is not zero probability. This is the impossible position that Italy's Department of Civil Protection now finds itself in. They have a scientific model with a date range. They have an increasingly stressed volcano, and they have 500,000 people living directly on the target. Their evacuation plan is one of the most complex ever devised. It divides the red zone into sectors, with staggered evacuation windows, attempting to funnel hundreds of thousands of cars and buses out of the densely populated area in 72 hours. But anyone who has ever been in a Naples traffic jam knows what a fantasy that is. On a good day, it can take an hour to move a few miles. In a panic, with every single person trying to flee at once, the roads would become parking lots. The science has done its job. It has provided a warning, an incredible, specific, data-driven forecast of a geological failure. Professor Kilburn's a model of a weakening crust, the Ings map of an active magma system, and Dr. Zaccagnino's calculation of a finite-time singularity all point to the same conclusion. The ground is going to break, soon. Campi Flegrei isn't a cautionary tale. Not yet. It is a live experiment in risk, psychology, and the limits of engineering. The people of Pozzuoli live with the rumbles every day. They watch the cracks in their walls grow. They see the harbor rising out of the sea. They are the inhabitants of a city that exists on a geological hair trigger. The mathematics are clear. The physics are undeniable. The clock that started ticking 20 years ago is now in its final minutes. What happens when the alarm finally sounds is no longer a question science can answer. The calculations are done. The deadline is set.